We should probably go ahead and get started. What questions do you have?
Um, can you explain mole?
Yeah, yes, sir. Okay. I will concede that this usually confuses students, but
What's that?
just mole, like in general, like mole confuses students. So it shouldn't though, because all mole is a number, and there isn't anything else to it. So I mean, there's a few things we need to talk about with it, but let me go over here, share that. We talked about, Sarah and I talked about this on Monday as well, but I'm sure it's good to go over it again. The So a couple things. One, a mole is just a number, and so you use words to describe numbers all the time, like dozen or trio or couple
Yeah.
or like a gross, like not used very often, but it means 144. So the issue is this is just another one of those types of words that means a specific number. It's just the only real difference is this number is very large. So can you see what I'm writing there? All right, so really it's 602. That's 602 and 21 zeros. So it's a ridiculously large number. It's really just too big for us to even fathom how large it is. And Sarah, can you tell us why we have to use such a ridiculously large number?
Because the pieces are really tiny.
Nailed it. That's it. Like if if you wanted to have a whole bunch, like our house got built this fall. I don't know how many nails they used, but we found hundreds of unused nails just on the ground around it. So I don't, they must have used, I don't know, thousands of nails. So when we were talking about nails, I wouldn't have said they used, like 459 dozen nails, right? That doesn't even make any sense. That unit is too small. So I'd want to use a bigger unit. So I would say they used 15,000 nails or something like that. So, and it's because nails are small, you need a lot of them when you're building a whole house. So this number equates to a usable amount of atoms and molecules. And an easy way to talk about it is carbon. So if you had this many carbon atoms, you'd have about 12 grams of carbon. So how do I know that? I know that because the number on the periodic table underneath the C, it says 12.01, so I just rounded to make it simple. So that number underneath the C tells us two pieces of information. The mass of a single carbon atom in atomic mass units, but when is anybody ever going to ask you to go get a single carbon atom? Like, that doesn't make any sense. So
Can't even find it.
you need specialized equipment to get your single carbon atom. So if I wanted you to go get some carbon because we were going to do an experiment, then you'd need something like 12 grams. Like that's probably, I don't know, a quarter or a fifth the size of a charcoal briquette. And so that's a usable amount. And that 12 grams is that giant number. But nobody ever wants to have to write that number. So instead of writing that number down, we just say a mole. In the same way that you don't say you got 12 donuts, you say you got a dozen donuts. Even though it's not really that big a deal between those two.
The mole is not like a specific number. It's just a very
No,
large number.
it is a specific number. It's that number right there.
Oh, okay.
It has to be that number. So all of those numbers on the periodic table below the symbol, it's if you had a mole of oxygen atoms, that mole of oxygen atoms that you're holding has a mass of 16 grams. Because on the periodic table, it tells you 16. If I
It's
was
like when you're cooking, you don't count out each little particle of flour, right?
That's great. It's not like somebody
Right,
says,
yeah.
get 1,733 billion particles of confectionery sugar to make this frosting. They say, go get 3 cups of sugar, right? And so why don't they do that? Why don't they have you count out exactly the same right number? Because one, it would take you too friggin' long. Like you couldn't actually even do it, right? You'd be dead before you finish counting 3 cups of flour out particle by particle. And that same thing happens with this. Like if I tried to count out that many carbon atoms, the whole planet counting at the same time with me, it would take us, I think the number is 8 million years to count to that number. So I don't count to that number. The best way to reason why we do this is my brother and sister used to live near a store or used to live near Seaside, and so they go to the arcade all the time, and they get those tickets after doing skeet ball and stuff like that. When they handed in, they saved them for years, and when they handed in several 55-gallon garbage bags of them, do you think that poor kid had to count them? He took handfuls of them and he put them on a scale. And then he looked down on the scale and said, oh, this many ounces, so that's 600 tickets. And then he just kept doing it. So what this allows us to do is count by just massing something out. Like if you knew eggs, the eggs that your chickens were laying were each 4 ounces, and then you grabbed a whole bunch of eggs and then you weighed it and it said 40 ounces, well, then you'd know you'd had 10 eggs. So it's a way to count something without actually doing the counting. Does that make sense? So why do we have to count them in the first place? The reason we're forced to count them is if I want to take magnesium and react the magnesium with sulfur, the compound that I'm going to make is magnesium sulfide. Okay? So every single time I react a magnesium to make magnesium sulfide, I need 1 sulfur. We okay with that? Like one of these and one of these makes one of those. Okay? But if I had 10 grams of this and 10 grams of this, do I make 20 grams of this stuff over here? And the answer is no. The reason is because this has a mass of about 24, and this has a mass of about 32 grams. So if I had 10 grams of sulfur, I have actually less sulfur atoms than I do magnesium atoms. Does that make sense?
Mm-hmm.
You okay with that, Sam?
Yeah.
Like grapes and oranges. If I had 10 pounds of grapes and 10 pounds of oranges, I'd have a hell of a lot more grapes than I would oranges, right? So knowing the mass doesn't do anything for us because the chemistry is not based off of mass. It's based off of I need one of these and I need one of these to make one of these. And the example we talked about last week also is bicycles. So I need 2 tires and 1 frame. That's how I build the bicycle. And I need 1 set of handlebars. Nobody's going to say, like down at the bike shop, Dirty Fingers, when they get like a huge shipment of bikes in, Miles isn't going to tell Mitchell, yeah, we've got 68 pounds of tires back here and 98 pounds of frames. He's going to say, yeah, we've got 10 frames back here and we've got, 39 tires or something like that, because you can count them. but we can't count atoms and molecules because they're just too darn small. So instead, we count them by figuring out what their mass is and then doing a calculation to figure out how many actually moles we have. So let's do that calculation real quick. Let me clean up some of this up top here.
What I thought was kind of interesting is that we look at these in like singular parts, right? So like you need one of this to make one of this, but in reality, no one is ever making anything with one atom.
Sure.
Well, because you told me that you can't even catch an atom, like nobody's even
well, we could
photographed one.
No, we can't. We can't photograph them, but that does not mean that we can't isolate a single atom. Just because we can't see it doesn't mean we can't actually isolate it. I know that seems counterproductive or counter reasoning.
How do you know you've isolated it if you can't see it?
Because I know what its mass is, and I know what its charge is. I have a device. We have devices that can detect the mass, momentum, and charge of any given particle. So we can actually like direct single particles at stuff. Everything past uranium on the periodic table is man-made. How did we man-make it? We set some substance at the end of a long tunnel and shot atoms at it, individual atoms at it, and hoped that the nuclei smashed together and held on and made a new thing.
Is that the
Atom Smasher, CERN's collider, atomic collider.
Is that relatively new? I remember hearing a lot about
not.
like the God particle and
No, the God particle doesn't have anything to do with this.
Okay.
The finding stuff like that is more recent, but we've been making these particles. We've been making new atoms since World War II.
Oh.
Okay, so let's look at this for a second. I can't make 20 grams of this magnesium sulfide. How many grams could I make? So this is the calculation that I would do. I mean, I'm not going to use any decimal places or anything like that, just to make it a little bit easy. So if I have 10 grams of magnesium, and the molar mass of magnesium is 24 grams for 1 mole. Okay. So I have 0.42 moles. So I don't even have a half a mole. I've got 42% of what a mole is. And that's totally fine. I mean, you can have a half dozen, right? You can also have a half mole or a portion of a mole. So how did I do that calculation? Well, the 10 grams was given. That's the problem. The 24, where did that come from? The periodic table. Right underneath Mg on the periodic table, it says 24. And this is my way of doing calculations. So the reason I'm doing it like this is up top is a numerator and on the bottom is a denominator. So if I've got like an algebraic calculation like this, what would you do immediately?
Divide.
Well, tell me what you would actually do. Yes, you divide, but do what? Those b's would cancel out with each other, right? Because there's one in the numerator and one in the denominator. Well, there's grams of magnesium, and I should have completed this. I should have wrote Mg here. And there's grams of magnesium in the denominator, so they cancel each other out. So I just did a unit conversion. That's what this thing does for me. So this is my way of doing unit conversions. And if you ask anybody who's taken my class and then gone on to the nursing program, they'll say whatever you do, you should remember how to do these unit conversions the way he does them, because it's hard to pass a particular exam without being able to do these. Let's do a quick one that's super simple. 36 inches. So I want to know how many feet this is. All right, so what I know is in 12 inches, there's 1 foot. So I've got inches in the numerator and inches in the denominator, so the inches cancel out. So the only unit I'm left with is feet, so then 36 times 1 divided by 12 gives me 3. Okay? So you probably saw this, and it was probably called dimensional analysis. And when they did that, it probably did this. 36 inches divided by 1 times 1 foot divided by 12 inches, right? And I'm just making it easier. Less stuff to deal with. All right, so let me get rid of all this. Okay, so I've got 0.42 moles of magnesium up here. So now let's figure out how much, let's figure out how many moles of sulfur I've got. So I have 10 grams of sulfur, and on my periodic table it says 32 grams of sulfur is 1 mole of sulfur. Okay, so I'll cancel out the grams of sulfur with the grams of sulfur. So what's 10 divided by 32? So 10 divided by 32 is 0.31 moles of sulfur. And this was moles of magnesium. So what did this just do for me? It took my mass and counted it. That's what I need to know. Are we okay with that?
Can you
Yeah.
explain a little bit further?
Yeah, let's look at this another way. Let's say that I had 10 magnesium atoms, okay? And I had 5 sulfur atoms. How many of these magnesium sulfides am I going to be able to make? 5. Only 5, right? Because as soon as I've made 5, I just used up all of my sulfurs. So I would have 5 leftover magnesiums after this reaction was over. We okay with that?
Yeah.
Yes? That wasn't a super
Yeah.
confident yes.
Kind of.
So what's wrong with this? What's confusing?
And I'm just adding them. I guess I'm just trying to figure out how to make them equal.
You can't make them equal. The reaction is 1 magnesium and 1 sulfur makes 1 magnesium sulfide. That's the whole reaction. So if I've been given 10 magnesiums and only 5 sulfurs, I've been given 5 extra magnesiums because I can't use them. Because
Oh,
once
okay.
I've made 5 MgS's, I have no more S's. So then all I have are leftover Mg's. Does that make sense?
Yeah. Okay.
Okay, so let me erase this. So what we just showed is we have 0.4 moles of magnesium and 0.31 moles of sulfur. Now, I know it's a little confusing because it says moles, but it's just a number. I mean, I could write whatever 41% of 6.02 times 10 to the 23rd is, but that would be even more confusing. Okay, this is like saying I've got a half a dozen bananas and I'm gonna put that together with a quarter of a dozen oranges to make a fruit salad. I don't know. That was a bad analogy, but whatever. How many MgS's am I going to be able to make? What number do I need to put in front of the MgS? Why is it 0.31?
Because if you have more magnesium, then you've got a completely different chemical.
No, I don't have a completely different chemical. My chemical can't change. So I showed up with 41 magnesiums and I showed up with 31 sulfurs. So how many MgS's can I make? 31. Why? Because the moment I've made 31 MgS's, I don't have any more S's. I've used them all up. Do we see that?
Yeah, we can't add more to it.
I can't add more S's to the MGs because I don't have any more. All of them have been turned into MGS. So what do I have left in my container? I have these 31 MGSs and 10 magnesiums left over. So
The
what
10 magnesiums won't stick to the MGSs.
apps 100% no way, not possible. Utterly
I want to ask
impossible.
why, but it's off topic, so I won't.
It's not off topic. If I gave you
Okay.
a bicycle and handed you three wheels and said put them on there, what would you do? You'd put 2 tires on there and then look at me and like, no, I can't do that. Or if I gave you 4 tires and handed you a tricycle frame and said put these on there, what would you do? You'd put 3 wheels on and then that's the end of it. The 4th one can't go on. The formula for MGS is MGS. It cannot be MG2S. It's impossible.
Does it become something different when it's MG2S?
I'm telling you, it cannot be MGS. It's not possible. There's no possibility of that happening. Like that
Right.
molecule doesn't exist in the universe.
Okay. And does that have to do with the whole, with the electrons
Yep.
lining up and there not being any extra space and they don't want anything else?
Yep.
Yeah?
Yes. When magnesium, this is off topic, but when magnesium forms a compound, it becomes +2, and sulfur becomes just a second. That was just terrible penmanship. And the sulfur becomes a -2. So they just smash together, and that's it. So if I tried to put another magnesium on there, then I'd have +2, +2, -2. So my overall charge would be +2. That's not possible. It has to be 0.
Right.
So what's the formula for table salt?
No idea.
NaCl, sodium chloride. Why? Because sodium gave away that 1 electron and became positive, and chlorine accepted that 1 electron and became negative. So I have a +1 and a -1, and that equals 0. I can't put another sodium on here because then this whole thing would equal +1, and that's not allowed. Whoa, just lost everybody. Did you just switch to, you just lost what I was, yeah, sorry.
Yep.
I hit a button. Where is it? There it is.
Be right back.
Okay. Okay, does that make sense? More sense? Can we figure out how many grams that 0.31 MGS is? Yeah, we can totally do that. Let's do that. Okay, so I know I've got 0.31 moles of MGS. And for every 1 mole of MGS, I've got some number of grams of MGS, and that works out to be 56. So where the heck did that number come from? It came from this number on the periodic table says 24 grams, and this number on the periodic table says 32 grams, and that adds up to 56. So that's my molar mass of magnesium sulfides, meaning if I had 6.02 times 10 to the 23rd of these MGSs, I'd have 56 grams of MGS. So this is 0.31 times 56. So I will be able to make 17.36 grams of MGS. If I start with 10 grams of sulfur and 10 grams of magnesium. And then what that tells me is I'm going to have a leftover 2.64 grams of magnesium. How do I know that? Because I put 20 grams of stuff in the container, and I have to have 20 grams of stuff in the container when I'm done. And I am positive that 17.36 of it is this. So all the rest of the stuff that's in the container is my leftover magnesium. And that leaves 2.64 grams of stuff that's magnesium. So why is this kind of stuff important? Well, the baking analogy is you walk into the kitchen and make chocolate chip cookies, and somebody took a dump truck and dumped sugar in front of your house. Like, did anybody need to do that? You were going to make 3 dozen chocolate chip cookies. Do you need that? Dump truck of sugar in front of your house? No, it's stupid. So this allows a chemist to figure out how many grams of this substance and how many grams of this substance do I actually need. So when I react them together, they'll basically run out at the same time. So let's do another example here. Na solid plus Cl2 gas turns into NaCl solid. I put a 2 here and I put a 2 here to balance everything out. So that's how you would make table salt if you had elemental sodium and elemental chlorine. All right? Just trust.
You have that's an S under the N and A.
Yeah, let me.
S is
Here, let's do this.
solid,
Let's do this.
and then
Sodium. And sodium is a solid on the periodic table. If you look at it, oh, this table doesn't show you that. Well, if you had a better periodic table, the periodic table would tell you that it's a solid. Okay, so, and then if you had chlorine, it's a diatomic, and naturally found, it's a gas. And then when I put these things together, I get table salt, which you know is a solid. I have to balance this because there's 2 chlorines on the left, so I need 2 chlorines on the right. So I'm going to put a 2 here. And now I just made 2 sodiums on the right, so then I need to put 2 sodiums on the left. So if I wanted to make this reaction happen, I'd have to put 2 sodium atoms in a container with 1 Cl2, and then I could get myself 2 sodium chlorides. All right, so what I want to say with this is that right there, elemental sodium, if you put that in your mouth, your head would explode. The water would react with the sodium to make hydrogen gas and energy, and your whole face would just explode. Like, I mean, it would kill you for sure. All right? What happens to you if you were to breathe chlorine gas?
Bad things. Would your lungs explode?
No.
Drown.
The
Ooh.
little air sacs in your lungs would be torn apart by the chlorine, and then you would just start bleeding, and your lungs would fill up with your own blood until you drowned. So those are 2 terrible things, right?
Yeah.
Explode my face, drown in my own blood, salt my fries. Like, this is one of the things about chemistry that I love. These 2 things kill people, and then the other thing we desperately must have for survival on the planet, because nobody can eat fries without salt. So if I was going to put sodium and chlorine in a container together, what would I want to make sure happened when the reaction was finished? Say again?
There's nothing left.
There's nothing left, that the sodium and the chlorine are gone. They run out exactly the same time. That when I'm making my chocolate chip cookies, when I'm done with it, I have no chocolate chips, I have no flour, I have no sugar, I have no salt. Everything has been used up. There is no ingredients left over. Obviously, it doesn't matter because the sugar or the chocolate chips aren't going to kill me. But in this case, it would kill me if I were then to go after that sodium chloride to salt my fries. The other 2 things, whichever one was left behind, would kill me. So
I need to make cookies tonight now.
uh,
I need
so
to make cookies tonight now.
is this okay? Is that going to happen?
No.
No, it won't happen. We know now that that can't happen because 10 grams of sodium doesn't mean the correct number of NAs to go react with 10 grams of chlorine. Why? Because this thing here, this has a mass of around, I don't know why I just wrote that. This has a mass of around 71 grams, and this has a mass of around 22 grams. Also, I need 2 of these to go with 1 of these. So the ratios are off, and the weight of each of them is off, right? I mean, you can't say, I'm going to use 2 cups of flour and 2 cups of sugar and 2 cups of chocolate chips and 2 cups of salt and 2 cups of butter and expect that to taste good. I put different amounts of each of those things in the same way I have to put different amounts of these things in. Does that make sense?
Mhm.
So why do we need to know about moles? Because moles tells us how many atoms or molecules we have, and that's how chemistry works. I need to know exactly how many of these things I have to react with these things so I can get this thing. Another super easy example that we talked about last time was hydrogen gas and oxygen gas makes water molecules. If I put a 2 here to balance out my oxygens and a 2 here to balance out my hydrogens, if I put 10 grams of this in a container and 10 grams of this in the container, I do not get 20 grams of water out of this because this thing has a mass of 2 grams per mole and this thing has a mass of 32 grams per mole. So I'm going to need to put 32 times as much oxygen by mass in the container as hydrogen because they don't have the same mass, and I need to put twice as many H's in as I'd put O's. So I have to know how many of those objects are there. So that's why
How
moles
did
are
they
important.
figure that out to such, I mean, that is, I mean, if you're working with something like sodium and fluorine.
People died. I'm not joking. I'm
Yeah,
100% not joking. So we didn't know about sodium until somebody took table salt, solid. V means voltage. So in that case, we're talking about electricity. So if somebody took electricity and ran it through table salt, you actually end up with that and that. You think that's a problem?
Yeah.
So a person's watching electricity run through this salt, and all of a sudden they're dying because they're breathing chlorine gas. They're like, what's that horrible stench? And then they keel over. And if there isn't anybody in the lab to drag them out, they just die. And that happened many
When
times.
was this discovered?
These experiments were done in the early 1800s. So the elements on the periodic table, a lot of them were created once we realized we could do this. We just started running electricity through stuff, which isn't the smartest thing in the world because you don't know what you're going to get out of that. Do you guys know what this formula is for? Something super common. Iron 3 oxide. This is just regular old rusted iron. So that orangey rust color, that stuff. So this one wasn't a big deal, right? When they ran voltage through this, they got elemental iron, so nice shiny new iron, and oxygen gas. Nobody died in the reverse making of this this rust. So it didn't kill everybody all the time when they did these kinds of things. It just killed them when they did stupid stuff like made chlorine or made fluorine or other toxic gases.
Is fluorine the same as fluoride?
Fluorine, fluoride. That little line was bad. Let me put that back up there normal. This guy has 7 valence electrons, and this guy has 8 valence electrons. And this one here desperately wants to get that 8th. So it will do anything it can to get that 8th. So if it's released into the environment and it runs into a piece of bacteria, it tears an electron off the bacteria, killing it, and then turning itself into fluoride.
Oh,
So is fluoride going to be hurting anybody? The answer is no. Why? Because it got the electron it wanted. So it's finished doing stuff.
The one's reactive and the other one is not.
The other one has already reacted, so it's finished, right? If you
It's
burn,
like a spent match.
yeah, it's exactly what I was going to say. You burn a piece of paper, it's not like you can grab the piece of paper and re-burn it, right? It's already been burnt. And what is it? What's happened to the paper? Electrons have been given to oxygens and taken away from carbons, and you have to do something to reverse that process. And we usually just let plants do it.
Mhm.
But this fluoride stuff isn't reactive like the fluorine because it's already gotten its electron.
so it's not a neurotoxin?
It's not a neurotoxin. No, that's an anti-vaxxer kind of thing to say.
Mhm.
Our body doesn't really do anything with it other than mineralize calcium on teeth. So why are dentists in favor, like why are people in generally in favor of fluorinating water? Because fluorine kills bacteria and viruses. So before this, you could drink tap water or well water and it could kill you. The first person that figured this out was a doctor in England. He did the first epidemiological, thank you, study. He didn't even know that's what he was doing, but that's what he did. And what it turned out was he had plotted all his patients and all his fellow doctors' patients of these people who had bacterial cholera. And then he put them on a map of London, East London. And it turned out every single one of them had drank out of this well. So they stopped drinking out of that well and the cholera went away. And then they dug down into the well and figured out that a housing complex right next door's septic system was dumping poop and pee into the well. So the cholera was just coming from people that live right next to the well.
Mhm.
So if you fluorinate the water, you can drink that poopy pee water. It won't kill you because all the bacteria in it's dead. And
What if
dentists,
there's no bacteria in it?
what?
And if there's no bacteria in it and then it's fluorinated, is it then?
Then it didn't need to be. Then it just tastes bad for no reason. Although you do get fluoride, and the fluoride will combine with the minerals in your mouth to make your teeth stronger. So that's why dentists are in favor of it. Doctors are in favor of putting fluorine in water so people don't get bacterial infections from groundwater. And dentists are in favor of putting fluorine in water because kids' parents are crappy about making kids brush their teeth, so they get lots of cavities. So if you have more fluorine in your water, you have less cavities. Period. End of story.
Don't eat junk food too.
Sure. Like people will say, well, people in Africa don't fluorinate their water and they don't have cavities. They don't have access to sugar. They just don't.
Don't eat crappy.
They actually eat better than you do.
Do you guys get the mole?
I feel better about mole. I mean, the whole reason we talk about the mole is because I need to know how many actual particles there are. I can't
Is there
know.
gonna be mole on exam 2?
Is there mole in chapter 3?
Yes.
Yes.
Is it more like a multiple choice question, or are you gonna have a
They're just
calculation to figure out?
they're just like the questions that you had for the first exam. Okay, something else?
I haven't gotten into chapter 4 yet, so I don't have any questions in regards to chapter 4.
We
Okay.
can talk about it though.
Yeah.
We can talk about Questions out of 4? Go for it. Like, what do you want to talk about? Did you other two get into chapter 4 yet? Sarah
No,
or
but
Young?
as soon as I find some numbers, I'll know what questions I need to ask you.
Some numbers? No. I don't know what that means.
Yeah. I am a very, very visual processor.
Me too.
And making that leap from like words to numbers to pictures is it's kind of a stretch sometimes.
This section is about hydrocarbons and about the energy that we extract from hydrocarbons, mostly in the form of heat. That's pretty much what this is about, and they just talk about it being energy from combustion. So it's probably the crappiest way for us to get energy out of stuff, but it's also a way that we know how to do. So that's why we do it. And we've got industries based off of the ability to make energy accessible via combustion. So, I mean, I know you've heard that word many times, but what does that mean to you? What does combustion mean?
Lots of heat.
Okay, so it's definitely an exothermic reaction. It's a reaction that's going to produce heat out.
Going to produce heat. Do you have to have fire?
No, you don't have to have fire. No, you don't. I mean, it's the way we usually do it, right? We usually add heat and then
that creates agitation.
Yes. So let's talk about this half a Post-it note. If I put a match on this half a Post-it note, do I have to keep the match on the Post-it note the whole time to get it to burn? No. I light this one corner of it, and then I can put the match out. And this combustion reaction produces enough heat to not only burn these atoms, but burn the next set of atoms. Does that make sense?
Mm-hmm.
And give me enough excess heat to do whatever it is that I want to do with it, like create lights, warm a house, power a car, any of those things. So when we talk about combustion reactions, we're talking about reactions that I put a tiny bit of energy in and I get a whole bunch of energy out. So much energy that I can use some of that energy to keep the reaction going until I simply run out of fuel. Like if you light a piece of paper on fire, it doesn't go out until the piece of paper is completely burned, right?
Unless it's wet.
Okay, well then we're not talking about a piece of paper, we're talking about a wet piece of paper. So why do we burn stuff? This chapter talks a lot about coal, which is a hydrocarbon, but why do we do that? What's the main reason we're burning coal and other hydrocarbons?
For energy? Push stuff or to...
Yeah, what do you mean by for energy?
When I think of coal, I think of like the trains that burn coal and they use this, like the steam and I don't know, coal to burn, coal to use in your little Weber fire grill to cook food.
Nobody uses coal for that. Charcoal and coal are not the same
yeah. That's what I mean. Yeah, that one.
Nobody said the most important use of coal.
I don't know, turning turbines?
Yeah, to do what?
Make energy, electricity?
Make electricity. All right. So this is how we make electricity. We literally boil water. So the reason that we use coal is there's a lot of it, and it's not hard for us to build the facilities to do this. So what we do is Can you guys see my cursor on the screen?
Hmm.
Yes.
All right, so I have this fuel source. So this coal comes in, they make it nice and finely ground, and they throw it into this boiler thing. So this is where it burns. When this water or when this coal burns, they've got these pipes that run over the top of it that are filled with water, and this is burning so hot that the water flashes to steam, really high temperature steam, high pressure steam, um, like 50 times the amount of pressure that you guys are experiencing right now than regular normal atmospheric pressure. So these pipes are filled with this steam, and then the steam comes down and hits a turbine. So that turbine is basically like
Pushing it.
like a wind turbine, right? So the wind turbines are pushed by wind, or like a mill to like mill grain is usually pushed by like water. So this is just a complicated version of that. And so the steam comes down this pipe and causes this turbine to turn. And on the other end of the turbine, there are all of these wires, and those wires are surrounded by a magnetic field, and that produces electricity. That's it. So all I need to do is boil water to turn this turbine. Do I need coal to do that? No. I could use natural gas, which is really just is a slightly cleaner version of coal. And there's absolutely no such thing as clean coal. Where does coal come from?
Dinosaurs.
Okay, but where do we actually get it?
The ground.
Ground. Is the ground clean? No, it's dirty. They don't do anything to it. They don't clean it. This is just coal they dug out of the ground and threw into a boiler. So whatever happens to be in the ground around the coal is also in that boiler. So bad stuff comes off, like sulfur-bearing products or nitrogen-bearing products that produce acid rain, or many other things. So
So what about the sun?
what about it?
Can the sun, well, usually where there's a lot of sun, there's not a lot of water, right? Because we get our electricity from the river, and the water's turning the turbines. So you'd think that where there's not enough water, they would be able to use the sun to heat water to generate electricity. And I mean, they probably don't even need to use water, do they?
No.
Probably.
What they
Some of
usually
that
use
water.
are mirrors and some kind of liquid metal.
Right.
But
And
we're not very good at that. As humans, we're not very good at building those facilities. And those facilities have what's the drawback of using that? What happens when it's not sunny?
sure,
So
you don't have
now it's
power.
December and your mirrors are covered in snow. So what do? The plant shuts down. I don't have that problem
Light
with
a
coal,
fire.
right? Light a fire, yeah, with my coal. So the people who design those plants have a problem, and the main problem is it's winter half the year, and they don't work as well. We don't even need those anymore. We can disregard this entire system and produce electricity directly using solar panels. Um, I don't know if you've heard about. I mean, obviously you know who Elon Musk is, and he's got a lot of ideas. And one of his ideas is to basically take a corner of Arizona, and Arizona is sort of a square, maybe a little bit more like a rectangle, with a little angly section at the bottom. And if we took a corner of it and covered it in solar panels, that's enough electricity for the entire United States. Like literally, you could remove every single electrical power plant in the United States, and a quarter of Arizona could power the whole country. The problem with that is it's not light 24/7, right? So what you would need to do is take sections of solar panels and then just put them around the planet, all the way around the planet, and then run wires off of them to all the different cities, countries, people's houses. So we could totally do that. But the people who are making money off of selling you coal to make electricity are still making money off of that. And they keep buying politicians to make sure that we don't do stuff like that. Trump got so much money from the coal people that he had the EPA roll back restrictions that the coal plants were required to do under the Obama administration. So now they can release as much crap into the atmosphere as they want, and nobody's there to check up on them. For two reasons. One, the law is less strict. And two, I don't know if you know this, but there are 5,000 jobs in the federal government that he's never filled because he's just too lazy. So there are all these jobs that you would expect people to have, and they just don't have them anymore. Nobody showed up to interview people to give them the jobs, so those jobs aren't there. So this gets super scary. It's not just people checking up on coal-fired plants. It's like people making meat. Like those people who inspect meat packing plants, they're not there. They don't have jobs. Why? Because he was too lazy to actually do it, to like hire those people. And the people that were there before didn't just get to keep their jobs. So after Trump took office and they were there ready in November to tell the people who came in what to do, how they do their jobs, and nobody showed up. So they just left. It's actually kind of terrifying. So we're not eating any meat that we don't get from people that we know in the gorge who raise our own cows and chickens, because there's a really good chance somebody's going to die, and it's already happened. People have already died from E. coli stuff from meats and produce. So not interested in being a part of that.
The E. coli stuff's been happening since before this administration, though.
Totally agree. But what you didn't find it in chicken and poultry and beef before this. This is a new thing. So let's. Do you guys have the book?
Yep.
Go to 167. Let's go to 167. Second, I'm looking for one other thing. They don't actually have the formulas that I was looking for in the prior pages. All right, it's not super important. So that table, have you heard those names before? They're on the table. I'm assuming you've heard one at least.
You mean like methane, ethane, propane, butane?
Yes.
Yeah.
Okay, so methane, ethane, and propane, those are the gases of hydrocarbons. So all of these substances, these are the first 8 hydrocarbons. And we call them hydrocarbons because they have carbon in them and hydrogen. And that's it. So super simple name. This comes from decaying organic matter. So the gas that comes out when you go poop is flammable. It's one of those gases. It's more than one of those gases. All organic matter decomposes. So like Princess Bride, is everybody familiar with the movie? The fire swamps? You haven't seen Princess Bride? Okay, so when we finish this class, you need to watch The Princess Bride like immediately. So swamps are really good places for matter to decay. And so they produce a lot of methane and ethane and propane, and it's very flammable. So these 3 are the first 3 hydrocarbons, and they're gases. So if you've got gas, like a propane grill, or your house actually runs its water heater or dryer off of gas, you're using methane, ethane, and propane. That's what natural gas is. So if they have an oil, if you find like a new oil find, that pool of oil at the bottom is going to be covered with ethane, methane, and propane gases. Which is why when they drill into it, there's this spike of stuff that comes flying out, and they have to cap it, and that stuff that's coming out is methane, ethane, and propane. So they'll capture those gases or do something really bad, which is just burn them off because they're annoying, because they're harder to work with than liquids. So we get those 3 gases, and then butane, because that's like in like a lighter. So you can see it inside the lighter and it's a liquid, but then when you push the little button, it comes out as a gas. So your hand is actually warm enough to turn it from a liquid into a gas. So the butane one is right on the border of being a liquid or a gas at room temperature. And then the other ones, those guys are liquid. So you know the one on the bottom, that's gasoline.
Mhm.
So these substances are what we've just basically been running our economy off for the last 120 plus years. And it's sort of like we had this huge savings account and we haven't been working all this time and we've just been using the savings account and we're kind of running out of the savings account. But also at the same time, we're using up our savings account, we're like destroying the environment. So doubly bad for us. So we don't need these things anymore. We literally do not need to run off of these hydrocarbons. There are lots of things that we could be doing besides this, but we're not. And the main reason we're not doing these things is because somebody else is making a ton of money off of stuff, and they're still making lots of money off of it. So we don't get the things that we need to get ourselves transitioning. Although the people, the more they understand about climate change, the more they want like a Tesla or a Prius or a Nissan Leaf. And so, I mean, 10 years ago, how many electric cars were there on the roads? Like full production electric vehicles.
Not as many as there were now, though.
There weren't any 10 years ago. The Prius existed, but that's not an electric car. That's a hybrid.
Cars.
So there weren't any, like none of the major manufacturers were making electric vehicles. And now we have electric vehicles out there. You see Teslas every day. You see Nissan Leafs every day. You see Chevy Volts every day. So those vehicles are around. And they're running off of rechargeable batteries. That's like an okay version. That wouldn't be my choice. So Bethany said something in the chat that said, I hear hydrogen power is our future. That's 100% true. The motors that we have right now, if they were modified a little bit, used a little bit different metals and changed the tanks and piping system, we could run hydrogen in our vehicles. So what does that look like? This is a combustion reaction. That's what this chapter is about, combustion. So do you remember this fire triangle from like the fire department showing up at your grade school?
Yeah.
So, sorry, I'm drawing here and I'm not sharing that page with you. A sec. Okay, so what did the fire triangle consist of? Fuel, heat, and what was the other thing?
Like a source or
No, oxygen.
oxygen, yeah.
So if you got rid of the fuel, you got rid of the heat, or you got rid of the oxygen, then the fire went out. So combustion is taking fuel and combining it with oxygen. That's all it is. So we've C8H18 plus O2 yields CO2 plus H2O. That's you driving around in your car. That's gasoline being combusted with oxygen to produce carbon dioxide and water. So if you run out of gasoline, the car stops moving. Why? Because you don't have fire anymore. Your car is running off of fire. If you were to run out of oxygen, the car would stop working because you need oxygen to pull apart the gasoline molecule to turn it into CO2 and water. All right? So what if my fuel tank in my car was filled with hydrogen gas and I used the same oxygen that I use in my car normally from the atmosphere? What's my byproduct? What do I get out the other end? What comes out of my tailpipe?
Exhaust.
Yeah, what's the chemical?
Oh,
It's water. That's it. Just water. Do you see how powerful that could be?
uh-huh.
So you go to the gas station, and instead of it being gasoline, there's just gas there. People right now already have cars that they fill up with propane. The car actually just runs off of the propane that you put in your barbecue grill. So instead of using the propane, you could use hydrogen gas. And so you pull up to the station and you put hydrogen gas in your car, and then you produce water molecules, and a whole bunch of heat, and your car drives along just fine. So what's the thing that people hate most about electric cars?
Having to charge them.
It takes a long time to charge the battery. This would take no time at all. This, you just fill it up in the same amount of time it take if you take your barbecue grill tank to the gas station and say fill this thing up with propane. It's filled up in a couple of minutes, and then you go along your way. So we could be doing this. The issue is, where are we going to get this from? Where are we getting hydrogen gas from? So the answer to that is, well, this reaction goes this direction and it goes this direction. So if I started off with liquid water, remember what happened when I ran electricity through stuff? What happened to the things that I ran electricity through?
Exploded.
They don't explode. They broke apart into their two pieces. Remember the table salt turned into NAs and CLs? This is going to turn into hydrogen gas and oxygen gas.
Are they doing this like in Iceland or Greenland?
They're doing
or
it all
something?
over the place. All over the place it's happening. The problem is it's not happening to a great extent. There aren't a lot of vehicles out there that can handle running hydrogen gas. But doesn't it?
Because that's a lot of pressure, right?
It's got nothing to do with pressure, it's temperature. The hydrogen gas burns at a higher temperature than the gasoline does. So some of the parts, if you were to just like put this in your car, it would melt parts and your car would break. So what needs to happen is they need to make the metal in your car out of better alloys. So that would cost a little bit more. But can you see how clean this is? Like, what causes your spark plugs to go bad? Carbon buildup on the spark plugs. Do you see any carbon here?
No.
The spark plug
No.
industry would basically go out of business, right? Because you'd put new
Yes,
spark
right.
plugs in the car when it was built, and they would never go bad. Nothing would ever happen to them. So does the spark plug industry want that? No.
No.
They want you to put new spark plugs in every 10,000 miles or whatever it is. What else would go out of business? Every oil refinery, right? They'd all go out of business because I don't need that anymore. How would this be a good thing? Well, there's no carbon dioxide anymore, right? So we're not producing greenhouse gases. So where do we get this electricity from? That's the tough spot. The best way to get the electricity, the best way to have this whole project happen is to run solar panels that run electricity through water that produce hydrogen and oxygen. Like, we could be doing this right now. And if we were in a true crisis mode, this is what we would be doing. It would just, everybody would be, I mean, you could do this at your house. Like the solar, there is a guy, do you guys know where Syncline is? Courtney Road on the other side off of SR14. What is that? Like 3 miles east of Bingen. So go 3 miles east of Bingen, and there's like a hiking, mountain biking spot there, and it's called Syncline. If you if you ride your bike all the way to the top, or you take the road up to the top so you can shuttle, you kind of go on this guy's property, and he doesn't really care. And he's got solar panels, and he does this at his house. He's off grid. He just takes water and separates it into hydrogen and oxygen, runs the hydrogen through a little generator, and produces his own electricity. So now all of a sudden, Portland General Electric is pissed off, right? Because you're not buying any electricity from them. The Army Corps of Engineers is mad because nobody's buying any electricity from the dam. Why? Because they don't need it. We don't need it. So what happens if there's an ice storm? Do you lose electricity at your house? Not that guy. He just goes out and knocks the ice off of his solar panel and goes back inside. That's it. There isn't anything to it. This is the way we should be doing things. There shouldn't have to be a grid. All you need is water transportation. As long as everybody has water, everything's fine. So
Solar's just very expensive.
say again.
Solar's expensive.
Polar's expensive?
Solar.
No, it's not. You're completely wrong. Solar electricity is 1/3 of the cost of coal electricity. A third.
I'm saying the startup cost is what I'm getting at.
It can be
For
like,
like install and stuff. I mean, if you stay on your property for like, 10, 20 years or stuff, you'll definitely make it up. But
sure.
like the
Okay,
monthly
so
cost,
let's say instead of giving Exxon several billion dollars, hundreds of billions of dollars per year, we just used all of that money to buy everybody in the country solar panels. What if instead of everybody having to put money in to have power lines being fixed and replaced and upgraded, we just stopped doing that and just put solar panels on everybody's house? That would cost a bunch of money for a little while, and then it wouldn't cost any money at all. We'd just be done with
it
it.
would make sense.
It would make sense, yes.
But it would lose big people, big money, so it's not going to happen.
Well,
Unfortunately.
it will, because those people are dying. That's it. The Koch brothers, one of them's dead, the other one's sick. Those are people that have been funding conservative talk radio and TV and candidates for 3 decades. I mean, I say this in class all the time. Things will change when more people die. Just the
There's
way it
a
is.
whistleblower from Portugal, I think. He's a hacker, hacked into what's her name, DeSantos.
Portugal's prime minister?
No, her father was the president of Angola for like
Oh,
27 years.
oh yeah. Okay.
And the level of corruption and just complete disregard for the people of that country is
Sickening.
atrocious. Uh, it, yeah, it is. It's incredibly sickening.
Friends around the world,
just-
unfortunately.
I'm just praying for the hackers, man. I just hope they get better and better and better.
So, if you flip to the next page, it shows you an oil refinery. And then on the next page, it shows you just like a mock-up of what those buildings inside the oil refinery are. So the way it works is you take oil out of the ground, crude oil out of the ground, you filter it so there aren't pieces of dirt in it, and then you heat it to a pretty high temperature, like 300, 350 degrees Celsius. And that takes all of this liquid oil, and it takes like 99% of it and turns it into a gas, like into the gaseous phase. And then this 1% actually is still just a liquid. And so what this thing is, since crude oil is a mixture of a bunch of different substances, this separates it into the different substances that are in the crude oil. So look at the bottom. Look at the bottom name on that fractional distillation tower. What does it say?
Asphalt.
Asphalt is oil. So with that thing, those C20, C16, C20, what that's saying is if you take carbons and you connect them up chemically together, so the molecule is 20 carbons long or longer, what substance do you produce? Asphalt. So think about all the asphalt that's on the planet. What happens when we run out of crude oil? We can't put asphalt down anymore. That it's just not going to be available to us. And that's why when it's on a really, really hot, sunny day, especially if it's a newer road, the road smells like,
Smell it.
it smells like, yeah, you smell the oil. Because what are you smelling? You're smelling oil, because that's what asphalt is. It's the dregs of a barrel of oil. So the molecules that are a little bit shorter than 20, they make it up a little bit. They actually turn into a gas, and they elevate themselves up to one chamber in this fractional distillation chamber, and then they turn into a liquid at that next level, and they take those off. And those things turn out to be like industrial lubricants. So like inside your car, there are bearings around the wheel, and those bearings are packed in something called wheel bearing grease. And that grease stays slippery even at really, really high temperatures, which is really good, because if it doesn't stay slippery, then friction increases and the temp increases, and then the wheel either seizes or actually catches on fire. Like I've definitely seen that before. Like a car gets burnt out because flames are shooting out of a tire, and that means the wheel bearing is locked up or the brake is locked up, one of the two, and produced so much heat that the metal caught on fire, which is obviously pretty scary.
Is that why my back tire is smoking?
Wait, what?
I've got like smoke coming out of my back tire
You need,
wheel well.
yeah, I wouldn't drive that. I would tow it someplace and that, or I would take that wheel off and take it someplace.
Okay.
Um,
Yeah,
actually,
because if you
Yeah,
drive that,
sure.
your
And
tire
they were
pops.
like, yeah, no, your suspension's fine, your brakes are fine.
where did you take it?
I took it to a Schwab.
Because they're idiots.
Okay, where's
I
she
am shocked that they didn't
Yeah.
find something. I like Taylor Automotive. I mean,
Okay.
he's
Okay.
super good, super trustworthy. He's just kind of hard to get into because everybody likes him a lot, and he's usually backed up. But he won't hose you over, and he'll just flat out tell you the truth, and he'll work on it till he gets it figured out. But that,
My husband said possibly your brake caliper seized.
yeah, that it's either the brake or the wheel bearing. But the easiest way to find out is if you've driven it, touch or kind of put your hand near it to see if it's hot. And if it's hot, you can't drive that car, or your car is going to catch on fire. Especially if it's a brake caliper or the wheel bearing is seizing, because that friction is going to produce so much heat. Literally, the thing is going to catch on fire. Like you might not think metal can burn, but metal can burn. It has a flash point.
Yeah, it's gotten pretty stinky.
Oh, if it's stinky, then it's almost certainly breaks.
Okay.
So it sounds like you've got,
It smelled like rubber at one point.
well, that's possible just because there's a lot of rubber down there. So you might have like partially melted like one of those accordion things that goes over the shocks, or maybe just a seal or something like on a shock or a strut or something
Yeah.
like that. But
Mhm.
it's probably just one of the calipers, like on the inside or the outside of the disc. Because if the whole thing was locked up, you wouldn't be able to drive. But if one of them, they collapse down on that, and if one of them came off but one of them stayed on, this thing's going to stay hot and it's going to stink.
Okay.
So as the molecules get smaller, they make it higher and higher up in this chamber, on this fractional distillation chamber, and then you recognize the names of those things. There's gasoline for jet planes. There's diesel. There's gasoline that they use, a gas that they use to make other gases. Then there's regular diesel, and then there's another jet fuel, and then there's gasoline. And you know the gasoline one because in between C5 and C12 is C8, and C8 is octane, and gasoline is octane. So on this list here, at least when we decided, the first internal combustion motor was a diesel motor. I don't know if you guys knew that. It wasn't a gasoline powered motor. Does anybody know the guy's name who came up with it is Diesel. His name's Otto Diesel. Do you have any idea what he was powering his diesel motor? What fuel he was using? It was 100% renewable. And it's too bad we didn't.
Oil.
It was peanut oil. Yeah. So his diesel motor runs off of peanut oil, which is why most people can do some slight modifications to their diesel and run it off of peanut oil or another kind of oil, because that's what it was originally designed to run off of. And sadly, we didn't stick with that design because the diesel motor is better than the regular internal combustion motor as far as like its longevity and its power. But when we found oil and decided we're going to use this as our fuel source, C8 was the thing that came out the most. So if I have a barrel of crude oil, of all of those different numbers, C1 all the way up to C20, C8 there was a ton of it. So they were like, all right, well, let's build a motor that can run off of this C8 molecule. So that's why we specifically use gasoline, octane, as our fuel source instead of like butane or hexane or something like that. And then 1, 2, 3, and 4 are at the very top. And so that's ethane, methane, propane. And since this thing's really hot, then the butane is actually a gas. So that's why it's up at the top. And so then it cools and they take the C4 out, the butane out, and use it for other stuff. And then C1, 2, 3, methane, ethane, and propane, that's used for natural gas or just like propane grill stuff. Yeah, if you turn on to the next page, you can see that it breaks down what percentage of stuff is what inside that barrel of crude oil. So of the 44-gallon barrel, 19.2 gallons of it is C8, which is octane, which is gasoline. So approaching half of it. All right. What was that like? All right, I think unless anybody has any questions, I think I'm gonna call it a night. So
No
anybody have any?
questions.
No questions? We're all
Gotta study more.
heard it again. That's always a good idea.